Good morning and welcome everyone to this course Physics 1. This course is generally made for undergraduate level BTech students. Myself, Gopal Chakraborty, Assistant Professor, Department of Physics, Greater Kolkata College of Engineering and Management, Baruipur. You can personally meet me at office premises, ground floor physics lab. You can send me your doubt or query at the given address that godphysics6@gmail.com or gopal.chakraborty_gkcem@jazzgroup.org. You can also visit to my YouTube channel. The link is given here for more video. So, I am the subject teacher for this course. Corresponding course pages are www.markoutexam.net or www.markoutwb.ac.in. You can also find the syllabus is uploaded there in the university page. The title of the course is Physics 1 and the subject code is BSPH 101. The category is under Basic Science course and this course has a credit 4 and 3 lecture per week, 1 tutorial per week. The course is generally made for first year BTech degree students. So, computer science, civil, mechanical, these departmental students will going to study this course for odd semester, and alternatively electrical and electronics departmental students will going to study this course, this subject Physics 1 in the event semester. Today I am going to discuss the topic force vibration. So in this chapter you will going to study force vibration in details, amplitude resonance, velocity resonance, power supply energy loss, quality factor, sharpness of resonance. So these are the main topics. So these topics are also under the module 1 mechanics. And prerequisite for this subject topic was fundamentals of mathematics and elementary idea of simple harmonic motion and damped harmonic motion. Course objectives are to understand the fundamentals of force vibration theory and explain the concept of resonance and its impact on the amplitude of an oscillator, to be able to mathematically model real-world mechanical vibrational problems. So after completion of this course, the course outcomes are that means students will be able to measure the maximum of amplitude and maximum kinetic energy. They will also able to identify, formulate and solve engineering problems related to this force vibration. They can perform and verify model executing force vibration of mechanical system and structure. Now, as I have already told you that you need the basic idea of simple harmonic motion or damped harmonic motion to understand the force vibration very clearly. Because in case of simple vibration or simple harmonic motion, what we consider that no frictional force or damping force are associated with that system. In case of damped vibration or damped harmonic motion, we cannot neglect or cannot exclude that frictional force or damping force or resistive force. So, in associated with the simple harmonic motion, these forces now comes into act, that is damping force or resistive force. In case of force vibration, in addition with that damping force, a periodic force comes into act which opposes the damped vibration. So this periodicity of the external force that must required in case of force vibration. So here also, when I am explaining this chapter, you can see that how I will solve the differential equation for force vibration. So this is the basic idea, that you need a periodic force to oppose the damped harmonic motion or damped vibration to derive the expression or equation of force vibration. So you can see here lots of examples are there for force vibration. So you can see the graph, it is clearly explained. So when you apply an external force itself, which is a periodic with the frequency omega t known as driven frequency. So here the application of this external periodic force make the system non-oscillatory to oscillatory, and it will achieve amplitude resonance or velocity resonance when that driven frequency, external frequency of oscillation will be equal to the natural frequency of oscillation. I'll show you in the next slide, but these are the examples of force vibration, where an external periodic force is applied to make the particle non-oscillatory to oscillatory. So here the examples are given for you. Now I will going to derive the differential equation for damped vibration to force vibration. I will show you step by step. So here I have considered a periodic force which is applied externally, that is, that value is considered as F equals to F sine omega t. So here, if you may remember that what is our differential equation for damped vibration? It was m d2x dt2 plus s dx dt plus kx equals to 0. Because no external periodic force is there to resist the damped vibration or damped motion. But here, that periodic force that we have considered that will oppose or resist that damped vibration. So here you can write simply m d2x dt2 plus s dx dt plus kx equals to f sine omega t, as I have considered. So rearranging, divide both sides by m, where m is the mass of the particle or object, you get d2x dt2 plus s by m dx dt plus k by m x equals to f by m sine of omega t. Now if you consider some constant, as I have already considered for my last two videos, that omega naught square equals to k by m, and s by m equals to twice b, and capital F by m equal to small f. So all these are constant basically. So if you substitute that value of this constant, what I will get, that is d2x dt2 plus twice b dx dt plus omega naught square x equals to small f sine of omega t. So this is basically the differential equation of force vibration. Okay. Now after constructing the differential equation for force vibration, again our objectives are same. You have to solve this differential equation, because you need some expression of x, which is the displacement. with respect to time. So how you will solve this differential equation? So this differential equation, equation number 1, it has two part of solution. One is CA part, another one is PI part. So for CA part, the solution is very simple, because for CA part, how we will solve this differential equation? Hopefully you know the procedure. That is, you just equate the right hand side is equals to 0. So if the right hand side of the equation 1 is equals to 0, this equation again becomes the equation for damped motion. So the solution, I have already derived this solution or derived this equation, how to solve this equation in my last video, okay, where I have discussed regarding the details of damped vibration. You may consult this video. So here I am considering, or directly I can write the solution. The CA part of this differential equation 1 is x1, that is equals to m e to the power minus vt sine of, within bracket, under root omega naught square minus b square t plus 5. So here solution equation number 2 gives the CA part of the solution of differential equation 1. Now how to solve this differential equation 1 for PI part, particular integral part? To solve this differential equation, let us consider the solution is x equals to a sine omega t minus theta. So this is a solution. So from there you can simply put the value of dx dt and d2x dt2. So dx dt will be a omega cos of omega t minus theta, and d2x dt2 will be minus of a omega square sine of omega t minus theta. So if you substitute this value of x dx dt and d2x dt2 in equation number 1, you will get minus a omega square sine of omega t minus theta plus twice b a omega cos of omega t minus theta plus omega naught square a sine of omega t minus theta, that is equals to f of sine omega t. Now how will solve this differential equation? Because your objective is to find out the value of the unknown constant a. So here in right hand side you can simply write by rearranging sine of omega t by sine of omega t minus theta plus theta. So it makes it a formula of sine of a plus b. So sine of a plus b means sine a cos b plus cos a sine b. So illustrating this, you can write a within bracket omega naught square minus omega square sine of omega t minus theta plus twice b a omega cos of omega t minus theta equals to f sine of omega t minus theta cos theta plus f of cos omega t minus theta sine theta. Now in both sides you can see that here sine omega t minus theta and cos omega t minus theta is there in case of both sides. So you can compare the coefficient of sine omega t minus theta and cos omega t minus theta. So if you compare the coefficient, what we will find? We will find that f sine theta equals to twice small b a omega, and small f cos theta is equals to a omega naught square minus omega square within bracket. Now if you take the square of these two and if you add, so it makes sine square theta plus cos square theta 1, taking f as a common. So what I will get? I will get that the value of the constant a is equals to f by whole under root omega naught square minus omega square whole square plus 4b square omega square. So this is the value of a. So substituting the value of a in the solution of x, that means x equals to a sine omega t minus theta. Now you can easily substitute the value of a, and the sum of these two equations for CI part and PI part will give you the total solution of X. Now, after getting the solution of the differential equation for force vibration, you have to know that what is amplitude resonance and what is velocity resonance. So before explaining the term amplitude resonance or velocity resonance, what do you mean by resonance? Okay, resonance means basically a particular condition you will get a maximum of something. So here, as I am talking about amplitude resonance, that means for some particular frequency or for some particular condition, you will get maximum of amplitude. Or in case of velocity, if some condition is satisfied or at some particular frequency of oscillation, you will find the velocity will be maximum. So that means corresponding kinetic energy will be also maximum. Okay, so first of all I will show you how you will derive the expression or the condition for amplitude resonance. You can see the derivation is here, and also the graph of amplitude with frequency is here. At particular frequency, a given sinusoidal excitation produces the maximum amplitude of oscillation in a resonance system. A phenomena in which an external force or a vibrating system force another system around it to vibrate with greater amplitude at a specified frequency of operation. So this is called amplitude resonance. That means where you will get maximum of amplitude. Now how will derive the condition of maximum amplitude? The process is very simple, because you have done this type of numericals in your mathematics chapter in your class 12. To define the condition for which a particular value will be maximum, so what you have done, you have always take the first order derivative, that will be equals to 0. That will give you that condition, and if you substitute that value, and if the second order derivative, that result is positive, that means it is a minima, and if the second order derivative results will give you negative sign, that means it's a maxima. So these are the procedure. I think you have remember that derivation. Okay, so here I will apply the same concept. So as we know, the value of A is equals to F by whole under root omega naught square minus omega square whole square plus 4b square omega square. So as here from the graph you can see that at particular frequency you will get the maximum of amplitude. So what you will do, you just simply take the first order derivative with respect to omega, and that value is equals to 0. So simply I have done here the derivative of A with respect to omega, that value equals to 0. So that gives me that 8b square omega minus 4 omega within bracket omega naught square minus omega square is equals to 0. From there I can find out that value of the omega, that means this is the particular condition or particular frequency of external periodic force that I have applied, that omega is equals to under root omega naught square minus 2b square. So equation 5 will give you the condition for which you can achieve amplitude resonance. That means maximum of amplitude. Now if you substitute the value of this condition from equation 5 to equation 3, you can able to calculate the value of maximum amplitude. So A maximum will be equals to A by under root 2B under root omega naught square minus v square. So this is the expression of maximum amplitude and amplitude resonance that you have achieved for a particular condition of the frequency, when the frequency, external frequency, will be equals to under root omega naught square minus twice v square. Now the next part, velocity resonance. So in velocity resonance you will achieve a maximum velocity for a particular condition. That means that for a particular frequency of applied external force you will achieve the maximum of velocity. So how you will derive this? I have already shown you that if x displacement value that I am considered, that x equals to a sine of omega t minus theta, so the velocity will be dx dt, that is a omega cos of omega t minus theta, where v naught is the instantaneous velocity, that constant value v naught equals to a omega, where a is the amplitude of oscillation. So now if you substitute the value of amplitude of oscillation, what you will get? You will get f omega by under root omega naught square minus omega square whole square plus 4v square omega square. So by rearranging you can write that f under root within bracket omega naught square by omega minus of omega whole square plus 4v square. So hence v0 to be maximum, what you can write? You can write the lower part of that equation or expression, that will be equals to 0. So from there, to satisfy this equation, you can write omega naught square by omega minus omega square whole square, that is equals to 0. So ultimately what you will achieve? The condition for velocity resonance, that is omega equals to omega naught. That means when the natural frequency of oscillation will be equals to the frequency of external periodic force, so that will help us to achieve the maximum of velocity. So this is our velocity resonance. So if you substitute the value of this condition in our first expression, you are able to get the velocity, maximum velocity, that is nothing but small f by 2b. Now the next part, that is power supply and loss of energy. So to calculate the power supply, P, capital P, that is denoted by, that is equals to instantaneous applied force into instantaneous velocity. So what is our instantaneous applied force? That is F cos of omega t or F sin of omega t. So instantaneous velocity will be F by mod of z cos of omega t minus theta plus pi by 2. So after substituting this value, as we know, the velocity dx dt, that can be written in terms of cos theta, that is d dt of b cos of omega t minus phi, that is equals to a by mod of z cos of omega t minus phi plus pi by 2. So ultimately we get the average power is this, that is given in my slide. Now how to calculate the average power? To calculate the average power, we have to take integration over dt, that is limit is 0 to t, so 1 by t 0 to t p dt. So if I substitute the value of p, capital P, what I will get? I will get that f square by twice mod of z 1 by t within bracket 0 plus t sin theta. So t will be cancelled out. So ultimately we get f square by 2 mod of z sin of phi. Now so this is the expression for average power. And what is the tan phi? Tan phi equals to omega gamma by omega naught square minus omega square whole square. So if again if we substitute this value, we get mod that that is z. Okay, p by z into x squared by 2 into mod z, that will be equals to average of power p. So here p is written as half of f by mod of z whole square into small p. Now, how we calculate the rate of work done by the dissipative force? Since the dissipative force or damping force acting on the force oscillation P dx dt, the rate of work done will be dw by dt, that is equals to instantaneous frictional force into instantaneous velocity. So here dw by dt, that is equals to p dx dt into dx dt. So this is after substituting that value, that this equation will get. So ultimately we'll get that is equals to dw by dt equals to p capital F square by mod of z square cos square of omega t minus phi plus 90 by 2, that means pi by 2. So that means what I will get now to calculate the average rate of work done, that will be equals to dw by dt equals to 1 by t0 to t dt. So if we substitute that value, ultimately we will get dw by dt, that is equals to half within bracket a by mod of z whole square into p. So this is the average rate of work done by that system executing force vibration. What is sharpness of resonance? So frequency response is a measure of the amplitude of an oscillation as a function of frequency. Sharpness of resonance is defined by the quality factor or Q factor, which is related to how quickly the energy of oscillation of the system decays. So the quantity omega naught by 2 del omega, so del omega is the bandwidth, that is omega 2 minus omega 1 is regarded as a measure of sharpness of resonance. So here I have shown you where the energy will be half of the maximum energy, so E equals to half of Em. So if we substitute that value, the energy, that is half of m f naught square by omega naught square del square plus 4b square, that will be equals to half of half m f naught square by 4b square. Now rearranging, we can write omega naught square del square plus 4b square, that is equals to 8b square. So from where we can write del square equals to 4b square by omega naught square. So omega is equals to plus minus twice b by omega. So 1 by del, that is called sharpness of resonance, and that is defined as plus minus omega naught by 2b. So this is our sharpness of resonance. Now the next one, that is quality factor or Q factor. The graph is here. The Q factor is a widespread measure used to characterize the resonators. It is defined as the peak energy stored in the circuit divided by the average energy dissipated in it per radian at resonance. Low Q factor Q circuits are therefore damped and lossy, and high Q circuits are underdamped. Q is related to the bandwidth. Low Q circuits are wideband and high Q circuits are narrowband. In fact, it is happened that Q is the inverse of fractional bandwidth. So you can write the quality factor with a ratio that is equals to omega naught by del of omega. So del omega is the bandwidth, frequency bandwidth, and that value is equals to omega 2 minus half omega 1, where omega 2 and omega 1 is the half power frequency. So half power frequency means where the maximum power is divided by root 2, 1 by root 2 of maximum power, or 1 by root 2 of maximum energy. So these are the half power frequency. So if you see the graph, you will get to this type of value, half power, at two particular frequencies. One is higher, that is omega 2, and lower one is omega 1. So omega 2 minus omega 1 will give you the value of the bandwidth, or del omega. So these are the reference book that I have considered. Now the evaluation process are same as I have discussed in my previous videos, that is, you have to appear for an external exam of 70 marks and internal exam for 30 marks, out of which you have to appear for an exam of 15 marks, you have assignment for 10 marks and attendance for 5 marks. So with this video, I have completed the chapter force vibration. Hope all of you have enjoyed and understand this force vibration. Thank you.